Hello everyone. So I wanted to give you an idea of how we collected the data for the first part of the work energy lab. So basically in this first experiment, we have an air track. It's on the incline, so I put this single weight underneath the single leg here, so it's at the incline. And we have a cart, right, that's going to accelerate down the air track. And the idea is to calculate how much work is done by the net force when the cart travels 1 meter. So basically, in this case, it'd be from like 40 centimeters down to 140, right? So 1 meter along the air track. Now, what are the forces acting on the cart? Well, if you think about it, right, as long as we ignore friction, that's why we're using the air track, there's only two forces acting on this cart. We have a weight acting down, right, towards the center of the earth, and then we have a normal force that the air track exerts upward on the cart. And we know that the normal force, since it's perpendicular to the displacement of the cart, it does no work on the cart. So the only force that's doing work on the cart is the weight of the cart itself. Okay? And you remember, it ends up being the weight times cosine of the angle that the weight force, that vector, makes with the displacement vector. And there's other ways of figuring this out as well. But the key thing is, it's a component of the weight that's doing the work on the cart. So in terms of data, what we want to get is the final velocity as the cart travels the 1 meter. So how do we do that? Well, we know the cart is starting at rest, right? So I started at 40 centimeters up here at rest. I'm going to release it. It's going to accelerate down, and I'm going to be able to get the time it takes to travel from the first to the second photo gauge. Okay? So if I know the displacement, right, think of it as delta x, think of x as along the air track, so that's 1 meter, delta x, divided by that time, that will give me the average velocity. But what we want is the final velocity, right? However, since we know that the acceleration is constant as it accelerates down the air track, then it turns out that the final velocity, since it's starting at rest, is going to simply be twice the average velocity. It'll be 2 times delta x over delta t. Okay, so I'm going to collect the time it takes that cart to travel the 1 meter. I'll do 10 trials, find an average. Then I'll do 2 times delta x, which is 1, divided by the average time. And that will give me the final velocity at this second photo gauge. Okay, and then later I'll show you how you calculate the work done by the weight of the cart itself. And we know from the work energy theorem that that work done should be equal to the change in kinetic energy. Well, the initial kinetic energy, since the cart is starting at rest, would be 0, right? There's no velocity, so 0. And then now that we know this final velocity here, we can figure out the final kinetic energy, which is going to be 1/2 times the mass of the cart times that final velocity squared. So the change in kinetic energy is simply the final kinetic energy. So the work done by the net force, which in this case is just going to be the work done by gravity, that's got to equal to the change in kinetic energy. So the whole goal is to verify that work energy theorem. Okay? So that's the idea of the first part of the lab.